Waves become larger as they approach the shore. That feels strange, doesn't it? When I think about ocean waves, I have two things in mind. On one side, the nice, small rippling waves at the shoreline, and on the other side, the large, rough waves in open sea. And that is almost the opposite of what the title of this video states. Still, it is correct. Waves do grow when they come closer to the beach. It can be explained using a complex set of equations describing the propagation of waves using a so-called linear wave theory. With a handful of simplifications, wave properties can be modeled pretty well. Like, for example, the propagation speed of an incoming wave. Although this equation looks daunting at first sight, it only really consists out of 4 easy parameters. We've got c, the wave speed, which we want to find, which by the way also appears in the function itself, making it explicit. Then we've got g, the gravitational acceleration, which is actually just a constant, being equal to 9.8 meters per second squared. Then we have d, the local water depth, and t, the wave period. So, linear wave theory provides us an easy, between quotation marks, an easy equation for the propagation speed of waves, based on, let's say, 2 simple factors: the water depth and the wave period. That equation is part 1 of the 3-piece puzzle, which explains why the title of this video is indeed correct. The second piece has to do with the propagation speed of wave energy, the so-called group speed. This happens to be a convenient ratio of the wave speed, always being somewhere between 50% for relative short waves and 100% for relative long waves. Again, the equation looks very daunting at first sight, but when you look at it closely, it's only really a function of the local water depth, the wave period, and the wave speed, which we have defined a minute ago. So that is puzzle part number 2. Now, on an interesting side note, for very long waves like tsunamis, this complex equation can be simplified to a reduced form, only depending on the gravitational acceleration and the depth. So, with a very fast calculation, we can get a good estimate of the speed of such a tsunami wave, which is pretty fast. So now, for the last part of the puzzle, we need to take a look at the amount of wave energy, taken as an average in time and space. Again, the linear wave theory comes to our rescue. It describes the average potential energy and the average kinetic energy, both as a function of the water density, let's say 1000 kilograms per cubic meters, the gravitational acceleration, 9.8 meters per second squared, and the wave amplitude, which is half the wave height. That's the last part of the puzzle, the amount of wave energy averaged over time and space. Okay, so let's connect these 3 puzzle pieces with conservation of energy. A wave will enter our so-called system and gives a certain amount of energy input per unit of time. We can define this flux using the average energy equation and the energy velocity, puzzle pieces number 2 and 3. By multiplying these two, we get our energy inflow per unit width. And this inflow of energy must be equal to the outflow of energy. So we can write this expression on both sides of the equation sign and cancel out some variables. When wave properties are known in deep sea, we can quantify the left-hand side of the equation to a fixed value. And then, for the right-hand side, we need to take a look at a modeled version of a beach. As makes sense, the water depth decreases when we get closer to the shoreline. And as we saw previously, the group speed is a function of this water depth. Thus, this can only mean one thing. The wave amplitude must change as well in order for the multiplication to stay constant. First, we see an increase in group velocity, so that matches smaller waves. But closer to the shoreline, the group speed plummets, which does result in growing waves. You can even see it in this footage that I used at the beginning of this video. The waves become larger, larger and larger until they break. That usually happens when the wave height is about 75% of the water depth. So, there you have it. Waves do become larger as they approach the shore. It may feel strange at first, but it's all explained using this phenomenon called shoaling.